Okay, so in this video I want to talk a particular example given originally by Fisher in 1922, and I read that in the book Generalized Linear Models by Göller and Nelder, about the use of generalized linear models or the derivation of the generalized linear models in some particular application. It's a very interesting example for me because it shows a constructive way how we can derive a link function that is not non-trivial in this example. So yeah, what's the example? So we're given a solution containing an infective organism depicted here. So the red dots should symbolize the infective organism, and our task is to estimate the concentration of this infective organism. So what's the idea? So we take our original solution, the concentration of our organism is rho 0, and then we dilute this solution step by step, and we take, for each diluted solution, we take a particular amount of that solution with volume V and put that on some agar plates, and then we count the number of agar plates that were infected by the organism and the plates that were not infected. We dilute in such a way that we always double the volume, so meaning the concentration is always divided by 2. Then what's the idea? So if you observed already that we denoted by rho 0 the original concentration we wish to estimate. We denote the volume of the solution. It doesn't really matter what's the exact value, but yeah, we can specify that in the experiment. And then finally the concentration of the diluted organism of the diluted solution is given by rho x, and this expression on the right hand side. Then let's come to the model now. So what we assume is that the organism is sort of uniformly distributed in that solution, and then we can make the assumption that the expected number of organisms on any plate is rho times x times v. Then we also can assume that the number of organisms is random, the number of organisms in a solution is random and follows the Poisson distribution. So let's denote with y the number of organisms in a solution of volume V, and then we have that expression here for a Poisson distribution given, where lambda, as usual, denotes the weight parameter, and k denotes the number of organisms. And in a Poisson distribution, this weight parameter also equals the variance and the expected number of organisms. Using our model assumption from before, we can now assume that this weight parameter is therefore rho x times v, and we have an expression for our Poisson distribution depending on the value that we want to estimate, the original concentration rho 0 that is somewhere hidden here inside. when we now have that distribution, we can write down the formula for the probability that we have no organisms in a solution, which is obtained by just plugging in 0 in the equation of the Poisson distribution, and then we obtain here this expression on the right side. That's simply the exponential of minus rho x times the volume. And we can also obtain the probability that we have at least one organism in the solution, which is just the complement 1 minus the probability here. So if we would know the original concentration, we could give for any diluted solution, we could give the probability of the agar plate being infected. So when we take that expression from the previous page for the probability that we observe at least one organism, and we plug that values in here, and let's call that quantity pi x, then we can do some reformulation steps in order to obtain on the right side a linear expression in x, the number of dilution steps, and on the left hand side we're going to have our link function for pi x, the probability of agar plate being infected. So how we start? We first we first bring the exponential on the right side, and then we take the logarithm. Now this quantity here is between 0 and 1, so this will be a negative number. So when we multiply it with -1, we obtain here a positive number, and conversely on the right hand side we also obtain a positive number. Then we can take again the logarithm to make that product into a sum, and plug in now the equation for rho x. Again, use the properties of the logarithm to make that into a sum, and finally we obtain the expression here on the bottom, where we observe that we have some constant factor here that depends on the volume that we can specify in the experiment and the original concentration that we wish to estimate, and then a linear term in x, the number of dilution steps. So now when we imagine that we have for each dilution step, we collect some data allowing us to estimate the proportion of agar plates being infected. Then now we can we are given from our modeling assumptions also this expression for eta by this double logarithmic expression, and we know that this eta by itself is described by a linear equation in the number of dilution steps, and we told just before alpha is the logarithm of the volume times the logarithm of the initial volume we want to estimate, and beta we know from the model is the log of minus the negative log of 2. So this illustrates a nice way how we can build a generalized linear model based on some initial assumptions about the system we wish to model.